Deep within the moon's core, something unexpected is happening that has renowned physicist Michio Kaku issuing urgent warnings to the scientific community. Recent seismic signals detected by advanced monitoring systems suggest our celestial neighbor isn't the geologically dead world we once believed. These mysterious tremors from the lunar interior could reshape our understanding of planetary evolution and potentially impact future Artemis missions. As humanity prepares to return to the moon, these discoveries reveal that our closest cosmic companion still harbors secrets that could change everything we thought we knew about lunar geology. The moon's hidden geological life. What if everything we thought we knew about the moon being a dead, inactive rock was completely wrong? For decades, scientists have described the moon as essentially geologically inactive, slowly cooling as it orbits Earth. This view portrayed our celestial neighbor as a silent, frozen world in the final stages of solidification with nothing interesting happening beneath its surface. Recent discoveries are shattering this long-held assumption. Advanced seismic monitoring has detected unexpected signals emanating from deep within the moon's core, suggesting ongoing geological processes that challenge our fundamental understanding of lunar evolution. These aren't minor tremors but significant seismic events that indicate the moon's interior remains far more dynamic than previously imagined. The implications extend beyond mere scientific curiosity. As NASA's Artemis program prepares to establish permanent human presence on the lunar surface, understanding the moon's internal activity becomes crucial for mission safety and success. These seismic signals could indicate areas of instability that might affect future lunar bases, mining operations, and long-term human habitation plans. Michio Kaku has been particularly vocal about these findings, emphasizing that what we're witnessing could represent the final chapters of the moon's geological story, a rare cosmic window that humanity is fortunate to observe and study before it disappears forever. Michio Kaku's scientific warning. Renowned theoretical physicist Michio Kaku has emerged as one of the most prominent voices, warning about the significance of recent lunar seismic discoveries. During his recent lectures and public appearances, Kaku has emphasized that these signals from the moon's core represent far more than routine geological activity. They could indicate fundamental changes occurring within our celestial neighbor. Kaku's concerns stem from the timing and nature of these seismic events. The moon's core, which scientists believed was in its final stages of cooling and solidification, appears to be undergoing unexpected changes that could have long-term implications for the Earth-Moon system. These aren't gradual, predictable processes, but sudden, measurable events that suggest something significant is happening deep within the lunar interior. The physicist has stressed that humanity exists in a unique cosmic moment. We're witnessing the moon's geological death throes, processes that operate on timescales we can barely comprehend. In another billion years, the moon's core may freeze completely solid, making current observations irreplaceable scientific data about planetary evolution. Kaku's warnings extend beyond academic interest to practical concerns about future lunar exploration. Understanding the moon's internal dynamics becomes crucial as humans prepare to return to the lunar surface and establish permanent settlements. The seismic activity could affect everything from habitat placement to resource extraction operations. NASA's advanced seismic detection systems. NASA's cutting-edge seismic monitoring technology has revolutionized our ability to detect and analyze lunar geological activity. The agency's latest instruments represent a quantum leap beyond the Apollo-era seismometers that first detected moonquakes in the 1970s, offering unprecedented sensitivity and precision in monitoring the moon's internal processes. The Farside Seismic Suite, scheduled for deployment around 2026, will be the first seismometer placed on the moon's far side. This positioning is crucial because it allows scientists to triangulate seismic events with much greater accuracy than ever before. The instruments are approximately 30 times more sensitive than their Apollo predecessors, capable of detecting even the faintest tremors from deep within the lunar interior. Additionally, the Lunar Environment Monitoring Station near the South Pole will provide continuous seismic monitoring for extended periods, unlike the limited-duration Apollo missions. This long-term observation capability is essential for capturing rare events and establishing patterns in the moon's internal behavior that might otherwise go unnoticed. These advanced systems might finally confirm whether the moon experiences slow quakes tied to core readjustment, similar to Earth's slow earthquakes that take days to subtly shift stress. Such phenomena could explain the mysterious seismic pulses that have drawn scientific attention and concern from researchers like Michio Kaku. The moon's internal structure revealed. So, modern analysis has revealed that the moon's internal structure is actually far more complex than we previously understood. The lunar core resembles Earth's in miniature, featuring a solid inner core that's surrounded by a fluid outer core, but with some unique characteristics that make it especially interesting to planetary scientists. The moon's inner core, for instance, has a radius of about 240 kilometers, and is primarily composed of iron, surrounded by a partially molten outer core that extends to about 350 to 360 kilometers. This structure generated a significant magnetic field billions of years ago, much like Earth's current magnetic field, providing evidence of ancient geological activity that has since diminished, but hasn't entirely ceased. What makes recent discoveries particularly fascinating is that the core didn't just switch off after cooling. Instead, it appears to be experiencing these final phases of activity that modern instruments can now detect. The entire moon is actually shrinking slightly in volume as it continues to cool, causing its brittle crust to wrinkle and form ridges or scarps. Some of these surface features are remarkably young in geological terms, like as recent as 200 million years old, indicating that cooling and contraction processes are still happening today. The ongoing seismic activity confirms that the moon is still adjusting to these internal changes, making it a dynamic rather than a static celestial body. Artificial intelligence uncovers hidden lunar secrets. One of the most remarkable aspects of recent lunar discoveries, honestly, involves artificial intelligence analysis of decades-old Apollo seismic data. Scientists have been feeding Apollo-era seismic recordings into modern machine learning algorithms, and the results are just revolutionizing our understanding of lunar geology. These precious recordings from Apollo seismometers have been sitting in archives for over 50 years, but they're now revealing secrets that were hiding in plain sight all along. When Apollo astronauts first deployed seismometers on the lunar surface, computers were room-sized and had less processing power than today's smartphones. The analysis techniques available in the 1970s were, well, primitive compared to what we have now. Modern AI can detect patterns and anomalies that were simply impossible to identify with 1970s technology. These sophisticated machine learning systems can distinguish between genuine lunar activity and instrument artifacts with, honestly, unprecedented precision. Patterns that human analysts dismissed or never even noticed are now being flagged as significant geological events. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has identified thousands of previously unrecognized seismic events, suggesting that the moon's interior is far more active than anyone realized. The Earth-Moon gravitational dance. The relationship between Earth and Moon is, in fact, a gravitational partnership that has shaped life on our planet in some pretty profound ways. The Moon acts as a gravitational anchor, preventing Earth from wobbling chaotically on its axis, and maintaining the climate stability that allowed complex life to evolve and thrive. Michio Kaku often emphasizes that Earth is unusually stable for a planet its size. Most planets would wobble chaotically, but the Moon holds Earth steady, sort of like training wheels on a bicycle. This stability has enabled the slow, steady development of ecosystems and eventually human civilization. Earth's tilt of 23.5 degrees, which is responsible for our seasons, would change unpredictably without the Moon's stabilizing presence. The Moon's gravitational influence goes beyond just creating ocean tides. It also creates these slight bulges in Earth's crust. This tidal flexing generates heat through friction, contributing to our planet's internal warmth and geological activity. It's kind of like Earth receiving a constant, gentle massage from the Moon's gravity, helping maintain its dynamic interior. Any changes in the Moon's core structure could, in theory, subtly influence this delicate relationship over geological timescales. The seismic signals that concern scientists like Kaku might indicate mass redistribution within the Moon that could eventually affect Earth's climate cycles, though, such changes would happen over thousands of years, rather than within human lifetimes. Risks to future lunar missions. As humanity prepares to return to the moon through NASA's Artemis program, understanding lunar seismic activity becomes a critical safety concern rather than merely scientific curiosity. The recent seismic signals detected from the moon's core raise important questions about the stability of potential landing sites and the safety of future lunar habitats. NASA's analyses have identified thousands of young tectonic ridges on the lunar surface, some potentially still active today. These ridges indicate areas where the moon's crust is under stress, creating potential hazards for future missions. Unlike Earth, the moon's crust lacks water circulation to heal cracks naturally, meaning that once fractured, the brittle lunar surface remains vulnerable to further instability. Future Artemis missions or private mining operations might inadvertently drill into areas near fault lines without fully understanding the consequences. The lunar regolith, the layer of loose, fragmented material covering the moon's surface, sits atop a complex network of faults and stress zones. Mining operations that disturb this delicate balance could potentially trigger moonquakes or surface collapses. The stakes are particularly high because lunar bases will be completely dependent on their structural integrity. On Earth, earthquake-damaged buildings can be evacuated while repairs are made. On the moon, a habitat breach could be catastrophic, exposing astronauts to the vacuum of space with little warning or escape options. The moon as a planetary laboratory. While we often think of the moon simply as Earth's companion, astronomers and planetary scientists view it as a perfect laboratory for understanding the evolution of countless worlds throughout the galaxy. The moon represents an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, providing crucial insights into how different-sized worlds evolve. Watching the moon transition from a molten core to a solid one offers glimpses into how exoplanets evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. One of the most critical factors for habitability is a planet's magnetic field, which shields its surface from harmful cosmic radiation. These fields are generated by molten, electrically conductive cores. The moon once possessed such a protective field, but as its core cooled, that protection faded. By studying the moon's seismic signals and understanding exactly how its core is solidifying, scientists can develop models predicting how long smaller rocky exoplanets might maintain their protective magnetic shields. This knowledge proves vital for identifying potentially habitable worlds among the thousands of exoplanets discovered by space telescopes. The unexpected seismic pulses from the moon's core provide new data points for these models, helping scientists understand planetary evolution across the universe. Advanced monitoring technology. NASA's next-generation lunar seismic monitoring systems represent unprecedented technological advancement in our ability to study the moon's internal processes. These instruments far surpass the capabilities of Apollo-era equipment, offering sensitivity levels that can detect even the most subtle geological events. The Farside Seismic Suite will mark the first time humans have placed seismometers on the hemisphere of the moon that never faces Earth. This positioning allows scientists to triangulate seismic event sources with much greater precision than previously possible. The instruments are 30 times more sensitive than Apollo equipment, capable of detecting faint tremors from deep within the lunar interior. The Lunar Environment Monitoring Station will establish long-duration seismic monitoring near the South Pole, where Artemis missions plan to build permanent human presence. Unlike Apollo instruments that operated for limited periods, this system will continuously monitor lunar seismic activity for months or years, essential for capturing rare events and establishing long-term patterns. These advanced systems might finally confirm whether the moon experiences slow quakes tied to core readjustment, similar to Earth's slow earthquakes that gradually release energy over extended periods. Such phenomena could explain the mysterious seismic pulses that have captured scientific attention and prompted warnings from researchers like Michio Kaku about the moon's changing internal dynamics. Advanced monitoring technology. Michio Kaku often highlights that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when we can witness and study the moon's internal dynamics before they cease forever. In another billion years, the moon's core may freeze completely solid, making current observations irreplaceable scientific data about planetary death. This perspective transforms lunar exploration from mere curiosity to urgent scientific priority. We're not just studying a neighboring world. We're capturing data during a unique period that will never repeat itself. The moon provides a live demonstration of how small planetary bodies evolve and eventually become geologically inactive. The seismic signals detected from the moon's core might represent one of the final chapters in a 4.5 billion-year story. As the lunar interior continues cooling, these tremors will become increasingly rare until they stop completely. Once the core solidifies entirely, the moon will truly become the dead world scientists incorrectly assumed it already was. Scientists often discuss the importance of being in the right place at the right time. In astronomical terms, humanity exists in an incredibly narrow window. After the moon has cooled enough for us to study its interior, but before it freezes completely and goes silent forever. This unique moment gives us opportunities not just to understand our nearest celestial neighbor, but to develop models applicable to countless worlds throughout the galaxy. The lessons learned from the moon's core could help identify potentially habitable exoplanets and understand how geological evolution affects their ability to support life. The mysterious seismic signals from the moon's core represent far more than geological curiosity. They're windows into planetary evolution happening in real time. Michio Kaku's warnings remind us that we're witnessing the final chapters of the moon's geological story, a rare cosmic opportunity that won't last forever. As humanity prepares to return to the lunar surface, understanding these internal dynamics becomes crucial for mission safety and scientific advancement. The moon continues teaching us about planetary evolution, magnetic field generation, and the delicate relationships that make life possible throughout the universe. Deep beneath the Swiss-French border, CERN's Large Hadron Collider has achieved something that honestly sounds like science fiction, creating conditions so extreme they may have briefly formed microscopic black holes. Now these aren't the massive cosmic devourers we know from space, but quantum-scale phenomena that exist for mere fractions of a second before evaporating in bursts of exotic particles. What scientists discovered in the aftermath of these experiments has, well, profound implications for our understanding of extra dimensions, quantum gravity, and the fundamental structure of reality itself. The theoretical foundation. The real secret behind microscopic black hole creation lies in some pretty cutting-edge theories about the nature of space itself. In standard physics, creating a black hole would require concentrating energy equivalent to around 10 to the 19th GeV, way beyond what any human-made machine could ever achieve. But theories involving extra dimensions like the Arkani-Hammett-Dimopoulos-Dvali or ADD model suggest that gravity might actually leak into hidden spatial dimensions while other forces stay confined to our familiar three-dimensional space. This would explain why gravity seems so much weaker than electromagnetic or nuclear forces. It's not inherently weak, but rather it's diluted across extra dimensions we just can't perceive. If this is true, it dramatically lowers the energy threshold for black hole formation, potentially bringing it within reach of the LHC's 13 to 14 TeV collision energies. The mathematical framework for these ideas really started to take shape around 1998 to 2000, when physicists like Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali proposed that our universe might have more than the four dimensions we experience. These extra dimensions would be compactified, curled up so tightly at every point in space that we can't detect them in everyday life, yet they fundamentally alter how physics works at the tiniest scales. CERN's experimental setup. The Large Hadron Collider represents, honestly, humanity's most ambitious attempt to recreate conditions from the earliest moments of the universe. Built in a 27-kilometer tunnel beneath the Swiss-French border, the LHC accelerates protons to 99.9999991% of light speed before smashing them together with unprecedented energy. The ATLAS and CMS detectors, which are just massive instruments containing millions of sensors, capture the spray of particles created in these violent collisions. When protons collide at such extreme energies, they create conditions similar to those existing just a fraction of a second after the Big Bang, when temperatures exceeded 1,000,000 billion degrees. The detectors track every particle emerging from these collisions, always on the lookout for signatures of new physics beyond the standard model. The CMS, or Compact Muon Solenoid experiment, has been specifically searching for microscopic black hole signatures ever since the LHC's early runs. These searches focus on identifying the distinctive particle showers that would result from black hole evaporation through Hawking radiation. The detectors have to distinguish between ordinary particle collisions and the unique signatures that would indicate space-time itself has temporarily collapsed into a microscopic black hole. the search for microscopic black holes. The CMS collaboration has, conducted extensive searches for microscopic black hole production throughout the LHC's operational history. During the 2010 run at 7 TeV Center of Mass Energy, scientists analyzed proton-proton collision data, looking for the distinctive signatures that would indicate black hole formation and subsequent evaporation. According to theoretical predictions, if microscopic black holes formed, they would immediately evaporate through Hawking radiation, producing a characteristic spray of subatomic particles. These particles would create specific energy patterns detectable by the CMS detector's sophisticated sensors. The evaporation process would happen in about 10 to the minus 27th seconds, an almost incomprehensibly brief moment. The search parameters focused on black hole masses ranging from 3.5 to 4.5 TeV, based on various theoretical models involving extra dimensions. Scientists looked for events where particles emerged in patterns consistent with black hole decay, including high-energy jets and unusual particle multiplicities that just wouldn't occur in standard particle collisions. While no definitive evidence for microscopic black holes has been confirmed in peer-reviewed publications, the searches have provided valuable constraints on theoretical models and continue to refine our understanding of what might be possible at these extreme energy scales. Stephen Hawking's encouragement. In 2009, renowned physicist Stephen Hawking visited CERN's underground facilities and made a remarkable statement that really captured the scientific community's imagination. While touring the Atlas detector with CERN Director General Rolf Hoyer, Hawking expressed his hope that the LHC would successfully create black holes, saying with characteristic enthusiasm, "I hope you'll make black holes." This wasn't just scientific curiosity. Hawking understood that creating microscopic black holes would represent a fundamental breakthrough in physics. Such an achievement would provide the first experimental test of quantum gravity, the long-sought theory unifying Einstein's general relativity with quantum mechanics. It would also offer direct evidence for extra dimensions and validate decades of theoretical work. Hawking's encouragement came despite ongoing public concerns about LHC safety. A lawsuit had actually been filed in the United States expressing fears that the collider might create dangerous black holes or exotic matter that could destroy Earth. The lawsuit was eventually dismissed on grounds that speculative fear of future harm does not constitute an injury in fact sufficient to confer standing. Hawking's support helped legitimize the scientific importance of these experiments, emphasizing that any microscopic black holes created would evaporate instantly through the radiation process he had theorized decades earlier. The Hawking radiation process. The theoretical framework for microscopic black hole evaporation relies on Stephen Hawking's groundbreaking work from the 1970s, which showed that black holes aren't completely black, but emit radiation through quantum effects at their event horizons. This process, known as Hawking radiation, happens because quantum mechanics allows particle-antiparticle pairs to spontaneously appear near the black hole's boundary. In this process, one particle from each pair falls into the black hole while the other escapes, carrying away energy and causing the black hole to gradually lose mass. For microscopic black holes, this evaporation happens almost instantaneously. The smaller the black hole, the faster it evaporates. A black hole with the mass of a proton would disappear in about 10 to the minus 27th seconds. The evaporation produces a distinctive signature, a burst of particles with specific energy distributions and correlations. These particles would include photons, electrons, muons, and potentially exotic particles not found in the standard model. The exact composition depends on the black hole's mass and the number of extra dimensions through which gravity can propagate. This rapid evaporation is crucial for safety. Any microscopic black holes created at the LHC would disappear before they could interact significantly with surrounding matter, making them scientifically fascinating but, practically harmless. Recent experimental developments. In 2024, CERN's High Radmat facility achieved a significant breakthrough by creating high-density electron-positron plasma beams that mimic the jets of matter and antimatter streaming from astrophysical black holes. The Fireball collaboration, led by researchers including Gianluca Sari, successfully produced plasma containing around 10 trillion electron-positron pairs, the highest density ever achieved in laboratory conditions. This experiment doesn't create actual black holes, but it recreates the extreme plasma conditions found in black hole jets, providing insights into how these cosmic phenomena behave. The research helps validate theoretical models of black hole physics using real experimental data rather than just computer simulations. Meanwhile, the search for actual microscopic black holes continues with increasingly sophisticated analysis techniques. Machine learning algorithms now scan collision data for subtle patterns that might indicate black hole formation and evaporation. These AI systems can detect correlations in particle tracks that human researchers might easily miss, potentially revealing evidence of quantum gravitational effects. The CMS and Atlas collaborations continue refining their search strategies, looking for soft, unclustered energy patterns. Subtle energy signals that don't form clear particle groups, but might indicate interactions with hidden dimensions or exotic physics beyond the standard model. Implications for extra dimensions. So, the search for microscopic black holes represents more than just an attempt to create exotic objects. It's actually a direct probe of space-time's fundamental structure. If these black holes can be created at LHC energies, it would provide the first experimental evidence for extra dimensions beyond the three spatial dimensions we experience every day. The existence of extra dimensions would totally revolutionize our understanding of physics, and could explain why gravity appears so much weaker than the other fundamental forces. It would also suggest that our familiar three-dimensional space is just a brain embedded in a higher dimensional reality, with gravity able to propagate through the full multidimensional space, while other forces remain confined to our brain. Different theoretical models predict different numbers of extra dimensions, from one additional dimension in some scenarios, to 6 or even more in others. The energy threshold for black hole creation, and the characteristics of their evaporation, would reveal crucial information about these hidden aspects of reality. And, such discoveries would also have profound implications for cosmology, potentially explaining dark matter and dark energy as manifestations of physics operating in extra dimensions. So, the microscopic black holes created at CERN might provide the first laboratory window into these cosmic mysteries. Safety considerations and natural experiments. So, before launching any high-energy experiments, CERN scientists, really took their time with extensive safety assessments, especially when it came to concerns about microscopic black hole creation. The main argument for safety actually comes straight from nature. Cosmic rays are constantly bombarding Earth's atmosphere with energies that, honestly, far exceed anything the LHC could ever produce. Ultra-high-energy cosmic rays can carry energies up to 10 to the 20th power electron volts, which is, wow, about 10 million times higher than the LHC's maximum energy. These particles have been creating natural collisions with atmospheric nuclei continuously, and Earth has experienced roughly 1 million of these impacts per square kilometer every year for its entire 4.5 billion year history. If microscopic black holes posed any danger at the energies CERN explores, nature would have already run these experiments countless times over. The simple fact that Earth is still here shows that any black holes created at these energy scales either evaporate harmlessly through Hawking radiation, or are just way too small to interact significantly with ordinary matter. And even if Hawking's theory turned out to be wrong and microscopic black holes didn't evaporate, they'd still pose no threat because of their incredibly weak interaction with normal matter. Such objects would just pass through Earth almost without any effect, kind of like the trillions of neutrinos that pass through our bodies every second without us ever noticing. Future prospects and upgraded searches. Looking ahead, as the LHC keeps running with upgraded detectors and higher luminosity, the search for microscopic black holes is, becoming more and more sophisticated. The high-luminosity LHC, which is expected to start up in the late 2020s, will actually provide 10 times more collision data, and that will dramatically improve our sensitivity to rare phenomena. Future experiments are going to use advanced artificial intelligence to analyze all that collision data, searching for subtle patterns that could hint at black hole formation. These AI systems can process vast amounts of data at the same time, spotting correlations and anomalies that would honestly be impossible for human researchers to catch manually. Then there's the proposed Future Circular Collider, a 100-kilometer ring that would operate at much higher energies than the current LHC, which could, in theory, give us a definite answer about microscopic black hole production. Running at energies up to 100 tera-electron volts, this facility would probe energy scales where extra-dimensional effects should, become really clear. Beyond just searching for black holes, these experiments keep pushing the boundaries of fundamental physics, seeking evidence of things like supersymmetry, dark matter particles, and other phenomena that could totally revolutionize our understanding of the universe. Every single collision gives us new data about the deepest levels of reality. The quest for quantum gravity. The quest for quantum gravity is really at the heart of this search for microscopic black holes. It's humanity's most direct attempt to probe the elusive theory that would finally unify Einstein's general relativity with quantum mechanics. Creating and studying these tiny objects would, for the first time, give us experimental data on how gravity behaves at quantum scales. These experiments could help resolve some of the most fundamental paradoxes in physics, like the black hole information paradox that's puzzled scientists for decades. If we can create microscopic black holes and study their evaporation in detail, it might finally tell us whether information falling into black holes is truly lost, or if it's somehow preserved in the radiation they emit, and the implications go way beyond just academic physics. Understanding quantum gravity could potentially unlock new technologies based on manipulating space-time, maybe even leading to advances in energy generation, transportation, or our understanding of consciousness itself. The microscopic black holes created at CERN might actually be the first steps toward a truly unified theory of everything. As scientists keep pushing the boundaries of what's possible, each experiment brings us a little closer to answering the deepest questions about the nature of reality. And whether or not microscopic black holes have actually been created, the search itself has already advanced our understanding of the universe's fundamental structure. So in the end, the quest to create microscopic black holes at CERN is really about more than just scientific curiosity. It's humanity's attempt to probe the deepest levels of reality itself. Whether these quantum-scale phenomena have been successfully created or, still remain tantalizingly out of reach. The search has already revolutionized our understanding of space-time, extra dimensions, and the fundamental forces that govern our universe. As technology keeps advancing and new experiments push ever deeper into the quantum realm, we're edging closer to answering the ultimate questions about existence itself. The universe's deepest secrets may finally be within our grasp. On July 1, 2025, astronomers discovered something extraordinary racing through our solar system. A massive interstellar object designated 3I/Atlas that dwarfs all previous visitors from beyond our cosmic neighborhood. This colossal traveler, potentially up to 12 kilometers wide, is moving at over 150,000 miles per hour on a trajectory that confirms its origin from another star system. Unlike the mysterious Oumuamua or the smaller comet Borisov, 3I/Atlas represents our largest confirmed interstellar visitor, offering unprecedented opportunities to study material from distant worlds before it vanishes forever into the cosmic void. The historic discovery. What started as a routine night of sky surveillance on July 1, 2025, became one of the most significant astronomical discoveries of the decade. The Atlas Survey Telescope in Rio Hurtado, Chile, operated by the University of Hawaii as part of NASA's Planetary Defense Network, detected an unusual moving object approximately 670 million kilometers from the Sun. Initially catalogued as A11PI3Z, this faint dot immediately caught astronomers' attention due to its peculiar trajectory and unexpected brightness. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, consists of 4 telescopes strategically positioned across the globe. 2 in Hawaii, 1 in Chile, and 1 in South Africa. These automated sentinels continuously scan the night sky, photographing the same regions multiple times to detect moving objects that might pose threats to Earth. However, what they discovered on that July night was something far more extraordinary than a potentially hazardous asteroid. Confirming interstellar origins. The confirmation that 3I/Atlas originated from beyond our solar system required careful analysis of its orbital mechanics and trajectory. Unlike objects native to our cosmic neighborhood, which follow predictable elliptical paths around the Sun, interstellar objects travel on hyperbolic trajectories, essentially one-way tickets through our solar system. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, explained that the object's velocity and trajectory definitively prove its interstellar nature. When astronomers traced its path backward through space, they found it approaching from the general direction of the galactic center, though pinpointing its exact stellar origin remains impossible due to the vast distances and timescales involved. The object's designation as 3I/Atlas reflects its historic significance. The 3I indicates it's the third confirmed interstellar object ever discovered, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas portion honors the survey system that first detected it, while its formal comet designation C/2025N1 indicates it was the first non-periodic comet discovered in the first half of July 2025. What makes this discovery particularly remarkable is the object's speed relative to the Sun, approximately 60 kilometers per second or about 134,000 miles per hour. This velocity is far too high for any object gravitationally bound to our solar system, providing conclusive evidence of its interstellar journey. Unprecedented size and characteristics. The sheer scale of 3I/Atlas sets it apart from all previous interstellar visitors. Current estimates suggest the object measures between 5 and 15 kilometers in diameter, making it potentially dozens of times larger than Oumuamua, which was only about 400 meters long. If confirmed at the upper end of these estimates, 3I/Atlas would be the largest interstellar object ever observed. Dr. Daryl Seligman, an astrophysicist at Michigan State University, who has been studying the object since its discovery, describes 3I/Atlas as shockingly bright despite its enormous distance from Earth. This brightness could indicate either exceptional size or an unusually reflective surface composition. The object's luminosity allows telescopes to observe it clearly even though it remains much farther from Earth than Oumuamua was when discovered. Early spectroscopic observations reveal that 3I/Atlas exhibits a reddish hue, similar to objects in the outer regions of our solar system. This coloration suggests the presence of organic compounds and complex hydrocarbons that have been altered by billions of years of cosmic radiation exposure. Perhaps most intriguingly, 3I/Atlas shows clear signs of cometary activity, including a faint coma, a hazy envelope of gas and dust surrounding the nucleus. This activity indicates the presence of volatile materials like water ice, carbon dioxide, and other compounds that sublimate when heated by solar radiation. Comparing the interstellar visitors. The discovery of 3I/Atlas gives astronomers their third data point for understanding interstellar objects, and honestly, it reveals some fascinating diversity among these cosmic wanderers. Each visitor has exhibited unique characteristics that, well, really challenge our expectations about objects from beyond our solar system. Oumuamua, discovered back in October of 2017, is still the most enigmatic of the three. Its extremely elongated shape, lack of visible cometary activity, and that mysterious non-gravitational acceleration, these all sparked intense debate about what it really is. Comet 2Y Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, turned out to be more conventional in its behavior. This object clearly showed typical cometary characteristics, including a visible tail and a composition similar to comets in our own outer solar system. 3I/Atlas, though, seems to bridge the gap between its predecessors while introducing a whole new set of mysteries. Like Borisov, it shows cometary activity, but its enormous size and those unusual brightness patterns definitely set it apart. Dr. Mark Norris from the University of Central Lancashire notes that 3I/Atlas doesn't look like either of them, which is crazy and exciting. The rapid succession of these discoveries, 3 interstellar objects in less than a decade after centuries of seeing none, suggests, such visitors may be far more common than we ever thought. Advanced Observational Campaign. The astronomical community has really mobilized an unprecedented international effort to study 3I/Atlas before it disappears into the depths of space. Unlike Oumuamua, which was discovered as it was already leaving the solar system, 3I/Atlas was detected early enough to allow extended observation campaigns using the world's most powerful telescopes. The James Webb Space Telescope, with its exceptional infrared sensitivity and massive 6.5-meter mirror, is perfectly positioned to analyze the object's composition and thermal properties. Webb's instruments can detect specific molecular signatures in the comet's coma and tail, potentially revealing the presence of water vapor, carbon monoxide, methane, and other volatiles that could provide clues about its origin. The Hubble Space Telescope continues to monitor 3I/Atlas using its ultraviolet and visible light capabilities, complementing Webb's infrared observations. Together, these space-based observatories provide a comprehensive view across multiple wavelengths of light, revealing details impossible to obtain from ground-based telescopes alone. Ground-based observatories worldwide have also joined the effort. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and numerous other facilities are tracking the object's brightness variations, rotation, and spectroscopic properties. Radio telescopes, including the Very Large Array in New Mexico, are monitoring for any unusual emissions that might indicate unexpected activity or composition. This coordinated global effort, honestly, represents the most comprehensive study of an interstellar object ever attempted, taking advantage of technological capabilities that just weren't available during previous encounters. Ancient origins and cosmic age. Recent research suggests that 3I Atlas may be one of the oldest objects ever observed, potentially predating our solar system by billions of years. Dr. Jesse Hopkins and his colleagues at the University of Oxford have developed models indicating that this interstellar visitor likely formed around an ancient metal-poor star in the galaxy's thick disk, a population of stars that formed when the Milky Way was much younger. Professor Chris Lintott, co-author of the Oxford study and presenter of BBC's The Sky at Night, explains that there's approximately a 2/3 chance this comet is older than our 4.6 billion-year-old solar system. If confirmed, 3I Atlas would represent a pristine sample of materials from the early galaxy, preserved in the deep freeze of interstellar space for eons. The object's ancient origins could explain its unusual characteristics. Unlike comets in our solar system, which have been repeatedly heated during passages near the Sun, 3I Atlas may be experiencing its first encounter with stellar radiation in billions of years. This pristine nature could account for its unexpected brightness and activity patterns. Dr. Michelle Bannister from the University of Canterbury notes that the gases released as 3I Atlas is heated by the Sun will test theoretical models about ancient comet composition. This temporal perspective transforms 3I Atlas from merely an interstellar visitor into a potential time capsule from the galaxy's youth. Trajectory and future encounters. So, 3I/Atlas is currently following a precisely calculated path through our solar system that will bring it to perihelion, its closest approach to the Sun, around October 30th, 2025. At this point it will be approximately 206 million kilometers from the Sun, just inside Mars's orbit, but still at a safe distance that poses no threat to Earth. The object's trajectory offers both opportunities and challenges for observation. During its closest solar approach, 3I/Atlas will be positioned on the opposite side of the Sun from Earth, limiting direct observation during its most active period. Dr. Astor Taylor, a graduate student in astrophysics at the University of Michigan, explains that despite the object's incredible speed, astronomers will have several months to study it. The comet will remain visible to large telescopes until early 2026, after which it will fade into the darkness of space, never to return. On October 3, 2025, 3I/Atlas will make its closest approach to Mars, providing an opportunity to measure how planetary gravity might subtly alter its trajectory. The object's outbound journey will take it beyond Jupiter's orbit by mid-2026, beyond Saturn by 2027, and eventually beyond the influence of our solar system entirely, resuming its eternal voyage through the galaxy. Scientific implications and astrobiology. The discovery and study of 3I Atlas carries, honestly, some pretty profound implications for our understanding of planetary system formation, the distribution of organic materials throughout the galaxy, and potentially the origins of life itself. As the largest confirmed interstellar object, it offers an unprecedented opportunity to analyze material from another stellar system in detail. If spectroscopic analysis reveals complex organic compounds within 3I Atlas, it would support theories that interstellar objects serve as vehicles for distributing the building blocks of life across the galaxy. This concept, known as panspermia, suggests that life's ingredients, or even life itself, might travel between star systems aboard comets and asteroids. The object's ancient age adds another dimension to its astrobiological significance. Materials preserved in 3I Atlas for billions of years could contain information about the early galactic environment when the first generation of planets was forming. Dr. Rosemary Dorsey from the University of Helsinki emphasizes that studying 3I Atlas provides insights into the role that ancient interstellar comets play in seeding star and planet formation across the galaxy. the object's composition and behavior could reveal whether the chemical ingredients necessary for life are common throughout the cosmos. The discovery also informs models of planetary system evolution, suggesting that the ejection of material into interstellar space is a common process that connects distant stellar systems through the exchange of matter and potentially biological information. Future detection and exploration. The discovery of 3I Atlas comes at a pivotal moment in astronomy, as new survey telescopes prepare to, really revolutionize our ability to detect interstellar objects. The Vera C. Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, creating a comprehensive movie of the cosmos that should dramatically increase the rate of interstellar object discoveries. Predictions suggest that Rubin Observatory might detect between 5 and 50 interstellar objects during its 10-year survey, with some potentially as large as 3I Atlas. The discovery also highlights the potential for rapid response missions to intercept future interstellar objects. While 3I Atlas was detected too late for any spacecraft to reach it, several space agencies are developing concepts for high-speed interceptor missions that could be launched on short notice when the next visitor is discovered. The European Space Agency has proposed the Comet Interceptor mission, designed to study a pristine comet or potentially an interstellar object. NASA and other agencies are exploring similar concepts that could provide direct sampling and analysis capabilities, opening entirely new frontiers in space exploration. These future missions could answer fundamental questions about interstellar objects that remote observation cannot address, including their internal structure, precise composition, and the processes that ejected them from their home systems billions of years ago. A new era of cosmic discovery. The arrival of 3I Atlas represents more than just another astronomical discovery. It marks humanity's entry into a new era of cosmic exploration where we can study material from distant star systems within our own solar system. Each interstellar visitor provides a unique window into the processes shaping planetary systems throughout the galaxy. As 3I Atlas continues its journey through our cosmic neighborhood, it carries with it secrets from an ancient star system that may have died billions of years ago. The data collected during its brief visit will be analyzed for years to come, potentially reshaping our understanding of planetary formation, the distribution of life's ingredients, and our place in the galactic community. The rapid succession of interstellar discoveries, from Oumuamua to Borisov to 3I Atlas, suggests that our solar system exists within a busy galactic highway where objects regularly travel between star systems. This realization transforms our perspective from viewing our solar system as an isolated island to understanding it as part of a vast, interconnected cosmic ecosystem. Future generations of astronomers will have access to increasingly sophisticated tools for detecting and studying these cosmic messengers. Each new discovery will add to our growing understanding of how matter, and potentially life itself, spreads throughout the galaxy. 3I Atlas may be just the beginning of a new chapter in human exploration of the cosmos, one where the universe comes to us in the form of ancient travelers from distant stars. The discovery of 3I Atlas opens an unprecedented window into the ancient cosmos, offering humanity its first detailed look at a massive object from another star system. As this colossal interstellar visitor races through our solar system, it carries secrets from a distant world that may have existed billions of years before Earth formed. The data collected during its brief passage will enhance our understanding of planetary formation, the distribution of life's building blocks, and our cosmic heritage. What other ancient messengers await discovery in the depths of space? Share your thoughts below, hit that like button, and subscribe to Future Facts for more incredible cosmic discoveries. Until next time, keep looking up.